The hardest part of any advanced math class is definition-based math. Not just calculations, but applying definitions. And so many things that you will deal with during your year of Algebra 2 are definition-based. They're not simply number crunching or even manipulating algebraic symbols. Anytime that things are based on definition, if you don't wrap your mind around that definition and its implication and how to use that definition, then all is lost. And to make it even worse, quite often, when you see the definitions stated, they're always stated in mathematical terms, and they use mathematical symbols. And it makes it extremely hard to pull sense out of it. And so one of the skills that you're trying to learn this year is the way to look at algebraic statements and read them as if they were simple grammatical statements. That was the key in trying to solve word problems, is being able to see the equivalence between a worded statement like 2/3 of a number as opposed to an algebraic counterpart, 2/3 x. So the first thing we've got is some vocabulary, and the first piece of vocabulary is the word argument, and a function's argument is the input of the function. So if I look at this first example, this is a squaring function. It's going to take something and square it. And so this is the type of function, squaring. So what's being squared? So the expression 2x minus 5 is the thing being squared. The 2x minus 5 is the argument of the function. So what about this thing here? F of x is equal to the square root. So this is a square root function. What's the argument? You fill it out, and then I'll tell you. Now, the absolute value definition is always stated formally this way. If you go to the internet and search absolute value definition, this is what you see. And how do you make any sense out of it? So here's the way that you read this in words. In words, you'd say the absolute value of an expression. And I didn't say x and I didn't say a number. I said an expression. So you might remember the idea that we have expressions, functions, and equations. And so it's just an expression. The absolute value of an expression is the expression itself if the expression is positive or zero. The absolute value of an expression is the opposite of the expression if the original expression is negative. That seems so confusing. So we'll do a couple of examples in a minute, but here's a little flow chart that also you can use. So you look at the argument of the absolute value statement beginning here. Look at the argument of the value of the absolute value, and then ask, is it positive? And if it is positive, just remove the absolute value bars and don't change the argument. Just leave it alone. But if you ask, is it positive? You say, no, it's not positive, it's negative. Well, then remove the absolute value bars and change the argument into its opposite. Or you might say it this way. If the argument's positive, leave it alone. If the argument's negative, change the argument to its opposite. So here's the way it works. Pi is about a 3. 3 subtract 2 has got to be positive. So if the absolute value of an expression is the expression itself if the expression is positive. So is this a positive expression down here? Is pi minus 2 positive? Yeah. Well, then its absolute value is the same thing as the original. Now, I know that the square root of 2 has to be smaller than, it has to be somewhere between 1 and 2. You're going to see a lot of square roots on this, and let me propose something to you when you do square roots. I'm going to come over here and make a little table that will be helpful to us. I know that 1 squared is equal to 1, therefore the square root of 1 is 1. 2 squared is equal to 4. Therefore, the square root of 4 is equal to 2. 3 squared is 9. Therefore, the square root of 9 is 3. So what that means is that if I see something like a square root of 7, then a square root of 7 would fit in about right here. And so a square root of 7 is somewhere between 2 and 3. So a square root of 2 is what I see in this problem here, and a square root of 2 would sit somewhere between 1 and 2. So when I look at this statement here, then I feel confident to tell you that the square root of 2 is smaller than 2, and take away 5, that's got to be a negative. If the argument is negative, then change the argument to its opposite, meaning when I remove the absolute value bars, it won't be the original argument, it'll be the opposite. Now, we shouldn't leave that in this form here. Notice to make something its opposite, I just put a negative out in front of it, and because it's a two-termed expression, I put a parenthesis around the whole expression. But the better expression would be either negative square root of 2 plus 5, or 5 subtract square root of 2. I would actually prefer the 5 minus square root of 2 because I like it to be a positive first if possible. It's not always possible. So when I see this, then this is the same situation. I'm convinced that negative 2 subtract square root of 2 is a negative expression. If the argument is negative, then change it to its opposite. So it's the opposite of the original expression. So that would simply be positive 2 plus square root of 2 would be the best answer. This time, though, notice that pi is positive. Pi plus 3 is definitely a positive thing. If the argument is positive, leave it alone. So the answer is simply pi plus 3. This last problem, square root of 7 minus 1. Notice again, I'm convinced that square root of 7 is bigger than 2, smaller than 3. So if I take 1 away from it, it's still a positive. So a freshman mistake, an 8th grader mistake, would be to put a plus sign instead of a minus 1 to a plus 1, and it would just be a total mistake. The correct answer here is the square root of 7 minus 1. Why? Because the argument is positive, leave it alone. So if the argument is positive, the absolute value is the same as the original expression. So here's something I pulled off of a released ACT test. If you're in the ACT prep, you may have seen this problem. So here's the way the ACT tests it. If A is less than B, then A minus B is equivalent to which of the following? So here's one of the things to think about. On our number line, A comes before B. And so you have to ask yourself, is A minus B positive? Is A minus B negative? And here's the general rule that you want to see. You're taking a bigger thing away from a smaller thing. A minus B is subtracting the larger thing, B, from the smaller thing, A. When you take something larger and you subtract something smaller from it, is it negative or is it positive? And the answer is it's negative. So what that means is that I have the absolute value of a negative expression. So if it's negative, change the argument to its opposite. So what is the opposite of A minus B? So the opposite of A minus B is this. So let's scan and see. Do we see a negative out in front of a minus b? Yes, we do. It's right there. So it's answer K. Now, there's another option that could have been the answer, and it could have been negative a plus b, or it could have been b minus a. So you have to watch out for all of those other algebraic forms that you could have used. But I want you to notice something at its core. This is just straight application of definition. And the ACT test is going to just test you, did you learn that definition and how to apply it? And if you did, well, this is a free problem for you. It just takes a second to do. But if you have some missed generalities in your head from Algebra 1, then you'll never get this problem. The second part of absolute value is used to describe a band of numbers on the number line. This is used a lot of times in programming. For instance, if you're trying to control the temperature of a warehouse environment between, say, 78 and 84 degrees, then we need to program the computers that operate their conditioning system in such a way that they trigger at those points. An absolute value is used to define a band of numbers along a number line. So let's zoom in a little bit here and talk about that. Suppose that I have a fixed point on the number line, let's say 6, and I'll box it in just to show I'm going to try to figure out how far another point is away from 6. So let's go out to 10. How far away is 10 from 6? And we would find that by doing subtraction. We'd do 10 subtract 6 is equal to 4. But what if I take a number on the left side of 6, say a number at 1? Then how far away would that be? If I use the same method where I take the point that's out there, subtract the point of reference, the 6, that would give me a negative answer. That would give me negative 5, but I want the answer to be positive because distance is always positive. How far is it from Canadian to Pampa? 46 miles? Well, what if you turn around and come back? Is it negative 46 when you return? So remember, from geometry, distance is always a positive value. So that's why we use the absolute value bars, and then we get only a positive answer. So you can tell that it's the subtraction here that is always used any time that I'm trying to compare two things on the number line. And I use the absolute value in the case where I subtract a bigger thing from a smaller thing, but I only want the positive answer. So there's the structure of absolute value defining how far two things are apart on the number line. So let's take a look at this example here. As a number line graph, the movable point is always x. So there's a point out here, maybe far out to the right, far out to the left, we don't know. It's just out there somewhere. But there's a fixed point at 4. And the fixed point, notice, is always the point that is being subtracted. So there's a fixed point at 4, and x is either out to the right or out to the left. So how far away is that movable point? And the distance is this expression that we see to the right of the absolute value. So specifically, I'll spell it out. The distance I'm concerned with is less than 7. Now, to put that onto a graph, I'm going to consider this. That was very strange, wasn't it? So what if I went 7 units to the right of 4? Where would I be? I'd be at 11. What if I went 7 units to the left of 4, I'd be at negative 3. So those 2 points are exactly 7 units away, but the distance I want x to be, the movable point to be, is less than 7 units away. That means that the negative 3 and the 11 aren't satisfactory points, but all the things in between are. Now, you should stop for just a moment and be sure that you read these bullet points and then start the number line or start the video back. Whenever I do this exercise, if I'll test the endpoints, I should get a statement of equality. So that's what I'll do now. The absolute value of negative 3 subtract 4 should give me the answer exactly 7, not less than, but exactly 7. Well, negative 3 subtract 4 is negative 7, and the absolute value of negative 7 is 7. So that's the equality that's mentioning. Now let's test the other endpoint. The absolute value of 11 subtract 4. Well, that's obviously a 7. So that proves that my graph is correct. Now let's pick any point in between negative 3 and 11. So just for fun, I'm going to pick a 6. So put 6 in for x. Is that less than 7? And that's what this is saying. A number from the solution region should create a true statement. So is this a true statement? Is the absolute value of 6 minus 4 less than 7? Well, 2 is less than 7, so this is true. And so that's the proof that my graph is correct. Now the second part here is to look at the x plus 3 and realize that distance is always a subtraction. And you have to be very adept at seeing additions as the subtraction of negatives. So x is always the movable point. The fixed point is the negative 3 being subtracted. And the distance is greater than or equal to 5. So let's make the graph. The fixed point is at negative 3. I'm supposed to be 5 units away or more. So the first thing we should do is we should think, where would we be if we were 5 units to the right? So 5 units to the right would put us at positive 2. What if we went 5 units to the left? That would be at negative 8. Now, the equality says that these should be plotted points, closed circles. But I want the actual distance of that movable point x to be more than 5 units away. That means further away than 2 to the right, and further away from negative 8, which would mean to the left of negative 8. So that's what the graph, I think, should look like. Now let's test it. So the first thing we'll do is to test the endpoints. So let's test a negative 8, absolute value of negative 8 plus 3. Well, the absolute value of negative 5 is equal to 5, and it's supposed to equal the number of the other side. Let's test the 2. So if I do 2 plus 3, absolute value, that would be an exact 5, so that checks. Now let's test a number in the solution region. Let's test something left of negative 8, let's say negative 10. So absolute value of negative 10 plus 3, well, that would be absolute value of negative 7. That's positive 7 on the absolute value. Question, is that greater than or equal to 5? And yes, it is. Now let's test something to the right of 2, say a 7. So let's do 7 plus 3 absolute value. Is that greater than or equal to 5? Well, 10 is greater than 5, so yes. So that's the way that you make a graph and check a graph. I forgot to do the interval notations on these graphs as the instructions said. You'll have to do that on your homework. So we're going to describe this graph using an interval notation. So interval notation, x is an element of. So it's always smallest first, comma, biggest last. So smallest number I see on this graph is negative 3, comma, biggest number is 11. If these were plotted points, I would use brackets, but they're not plotted points, they're open circles, so I use a parenthesis. So there's the interval notation for that graph. On this one here, there's 2 sections of graph. Interval notation always starts out with x is an element of, smallest comma, biggest. The furthest left point on this graph, no limit, negative infinity. The furthest right point, negative 8. On this section of the graph, negative infinity is not a plotted point, because negative infinity is not a number. But negative 8 is a plotted point, so we use a bracket. Then in union with, when there's a skip in the graph like you see here, it's the union of the left side and the right side. But again, remember, it's always left to right progression, smallest comma, biggest. So smallest number 2, biggest number, there's no limit, that's infinity. And infinity is not a plotted point. 2 is a plotted point. So your homework will also have those required interval notations. Be sure that you put those on your homework. Now, just to notice, because of the equal distances on either side of this fixed point, that fixed point is the midpoint. This is something you should have learned in your geometry class. When you're trying to find the midpoint of 2 points on a number line, you simply average them. So if I average 2 and 10, I do the addition, divide by 2. 10 plus 2 is 12, divided by 2 is 6. So the fixed point that's in the middle would be a 6. How far is it from 6 to 10? How far is it from 6 back to 2 on the other side? And the picture of this graph is the graph of all points that are less than 4 units away from the fixed point of 6. So the movable point x, the fixed point 6, and the distance is less than or equal to 4 units away. So the structure is always there minus here. And so the x point is out there moving somewhere. The fixed point that we're comparing to is the 6. It requires an absolute value in case the subtraction yields a negative. And the distance is going to be less than or equal to 4. I'll leave it to you to test to see if that's the correct statement, the same way we did the previous problems. So the fixed point is always this midpoint here. So we're going to average, again, the two midpoints. So we'll take the left point and the right point, add them together, divide by 2. That answer would be a 1. So how far is it from 1 over to 7? 6 away. How far is it from 1 back to negative 5? Again, 6 units away. So the movable point is x. The fixed point is the 1. And the distance away is greater than 6 units away. So here's our statement. There, the movable point x, minus here's the fixed point 1, absolute value in case it gives a negative answer, and the distance is greater than 6. So that's the way you do those. Good luck. I'll just tell you, you really have to sit with all of these concepts, especially things that are definition-based or something that's new that you've never seen before. And you solve some absolute value equations as Algebra 1 students, but you weren't forced to think about the about the absolute value definition, and you weren't forced to think about the absolute value as a way to describe a band of numbers on a number line. So there's a lot of new material here that you're really going to have to wrestle with. You won't be able to be successful unless you sit and contemplate these ideas by yourself until they begin to make sense.